In this first example with our second lesson in the introduction module, I encourage you to print out or otherwise obtain these handouts that go along with our presentation of the material. We'll use this approach extensively throughout the course, and really it's to enable you to be able to focus more on the content of what we're doing and thinking process, and not as much as on the transcription of notes, so to speak. Right? And we're going to use this pedestrian crossing example to illustrate a variety of basic concepts in probability that we will later then expand upon and use in great detail, not only as we get into modules 2 and 3 and 4, which are all probability modules, but as we get later in the semester and we start focusing in on applications of statistical and probabilistic models under a large umbrella called statistical inference. Right, so these basic notions and concepts will be are started here and are used then repeatedly throughout the course. Right, and in this particular example, we're going to look at a context from an engineering perspective of a busy one-way street, and perhaps it's also useful to think about this busy one-way street as a one-lane street. It's not necessarily all that important for us. We don't have to make that restriction in the numbers that you're going to be taking a look at, but it's a little bit easier to think about if we do it that way. Right? And the issue to be considered from an engineering perspective is whether or not to put in a pedestrian signal or a pedestrian overpass. And what we've collected on site is enough data to gather the following conclusion, and that is that the times between cars or vehicles, it doesn't matter whether it's cars or trucks, can be thought of as coming at us of one of 5 possible different outcomes: 3, 6, 9, 12, or 15 seconds. Of course, the actual data collection might be 3.258 or 6.49 or whatever, a real number, or what we might call in the continuous domain. But from a simple processing standpoint and trying to look things maybe at an initial design perspective, we've decided to lump or discretize the possible outcomes into only these 5, 3, 6, 9, 12, or 15. And we've also observed in our data and have concluded that these time gaps come at us in ratios of 1 to 2 to 3 to 2 to 1 with respect to these possible outcomes of 3, 6, 9, 12, or 15. So if you're looking at Chapter 2 of Montgomery and Runger, what you'll notice is they'll start talking about different events in an event space and possible outcomes for our random variable. Well, T would be our random variable. That's the time in between vehicles. That's the time available for a person to walk across the street or to somehow get across. Right? And so our possible outcomes are 3, 6, 9, 12, or 15. The question to be addressed is that we've documented in our study that a pedestrian requires exactly 8 seconds to safely cross the street. Now that's what we're going to do in this first example. In later examples, we'll begin to look at different times that it might take to get across the street and how does that change what we're ultimately going to be asking, which is really all about what's the probability of a safe crossing. Okay? And so there's a variety of ways that you might consider how you will cross the street. Our parents would probably insist that we actually wait until a vehicle passes and begin immediately afterwards, looking to make sure that the gap is appropriately long enough. Right? Well, we're going to sort of ignore a part of that, and we're just simply going to say that a pedestrian crosses immediately after a vehicle and that it takes them exactly 8 seconds to cross. And under those constraints, what's the probability of safe crossing if they do begin immediately and it takes them 8 seconds? Right? So that's the big picture question we're going to go after. Now, we're going to introduce some notation and some definitions along the way, so it's going to be more than just answering that specific numerical problem here. Let's go back again. The random variable that we're focused in here is this time gap t, with these 5 different possible outcomes that come at us in the frequency of 1 to 2 to 3 to 2 to 1. So that if we added up all the numbers, if we had 1 3-second gap, 2 6-second, etc., we'd end up with a total, that sum would be 9 different balls, so to speak, where each ball was printed with either 15 or one of these other 5 kind of numbers, right? So the chance that we would pull out a ball that had a 3 stamped on it would be 1 over 9. And we call that, when we have discrete values for our random variable, we call that the probability mass. And sometimes people will refer to that as PMF. Of course, just standing for probability mass function. The symbol that people will give to this is either a lowercase or uppercase. I prefer the lowercase p for probability, and then a subscript of our random variable, which is capital T here, and then because this is a function, we'll then have the parentheses, and in a sort of script or lowercase, we'll have then lowercase t. So the uppercase indicating the random variable, the lowercase being the functional independent variable, so to speak. And because it's a discrete variable and not continuous, you oftentimes will see a subscript of I on this argument to the function, t sub I, to indicate again that there are only discrete possible outcomes associated with this random variable. Right? So for the probability mass associated with 3 seconds, meaning the likelihood that we will have a 3-second gap is 1/9. And then that's just 1 divided by 9, right? 9 total balls in our bag, right? And 2 of those 9 would have 6 printed on them. 3 of those 9 would have 9 seconds printed on it. And then we go down to 2/9 and then 1/9. And note that if we add up all those probability masses over all the possible outcomes, then that total probability would be 1. And the total probability is always 1. And if you have a function where that's not the case, then you don't have a properly defined probability mass function. And indeed, we can use this property of probability mass functions to oftentimes then figure out what the parameters ought to be of the individual values. If this is in this case, we found these just by sort of brute force, raw consideration of the numbers, but say you had a functional description you wanted to consider with a various couple of parameters that had yet to be defined or determined, and we can use this property then to calculate sometimes what some of those constants or parameters are that distribution. Right? Now, this is enough actually in this particular problem to be able to answer the question, but we're right here, and so let's go also and define what the cumulative distribution function is. And in big picture context, that is all about the probability, now that's capital P, of our random variable being less than or equal to our outcome. And for discrete random variables, it's very important that it's less than or equal, not just less than. There's a critical difference. For instance, the probability that t, our random variable, is less than or equal to 3 is going to be, well, just 1/9. If it was less than 3, well, this number would be 0, because we have no balls in the bag that have a number that is less than 3 printed on there. Right? So go to the next one, probability that our random variable is less than or equal to 6 seconds. Well, then that would be 1/9 plus the 2/9, so a total of 3/9. And so we're going to continue to add this up. We go up to 6/9 and then 8/9, and we get to the last possible outcome, and that has to be also numerically equivalent to 1. Right, now that's how the cumulative distribution function will work for a probability mass function. Later, when we get to analyzing data and looking at histograms, and there's a way to process that so that it'll be a little bit different than this. But that's because when we process observed samples, those are subsets of the entire population. And here we are talking about exactly the population of time gaps, and therefore in our model, this, when we look at the probability that t, our time gap, is less than or equal to 15 seconds, the max possible value, and then that has to be the case that the cumulative distribution function ends up being 1 at that upper level. Okay. The other aspect of this to keep in mind is that the symbol that we often use for all this is a capital F, and then the random variable of interest as a subscript, capital again, and then the argument to the function t sub I, just like we had before. What you'll sometimes find, and your Montgomery and Runger authors, your textbook for this course, do this, is that they'll sometimes use, for the probability mass function, a lowercase f in replacement for the lowercase p. Right? I don't do that because I've learned in a whole set of other authors who use this lowercase f for continuous random variables versus they use the lowercase p for discrete random variables, and that's the additional information they're conveying when they choose to use that particular symbiology. Not all authors do that, and it's really, I suppose, not all that important, except for you need to be aware that some people are very careful and they have additional meaning that then gets attached to their symbols more than just a simple, hey, this is the probability mass function. Hey, there's more that's getting conveyed there. Right? We have, again, way more than enough information here to be able to address what our actual problem statement was, which is, what's the probability of safe crossing if we begin to walk immediately after a car passes, given that it takes exactly 8 seconds to cross. Right? And that vertical bar is a symbol for the word given. Right? This is also, in essence, what we call a conditional probability statement that we're going after as well. Right? So that's what we're really trying to do here, is that we're looking at probability of safe crossing given 8 seconds to cross. And since we're beginning immediately after then that a car comes, in other words, immediately at the beginning of the time gap, it's fairly obvious that, hey, you know, the 3 second time gap, there's no way we can get across. And the 6 second, no way that we can get across. But if we start at the beginning of a 9 second, we absolutely make it across. In fact, we make it across with 1 second to spare. So what this amounts to be then is, all we need to do is calculate what the probability is that our time gap is greater than or equal to 8 seconds, since it takes exactly 8 seconds to cross. Now, note you could write this as 1 minus the probability that t is less than 8 seconds. And again, the notion that it's a discrete random variable, we have to be very careful where we put the equal sign here. In this case, 8 seconds is enough to get across, so that equal sign has to be over here on this side, that t greater than or equal to 8 seconds. Right? And I get this whole 1 minus business all because, hey, if we look at all the different events, we have a total probability of 1. So if I'm looking at a subset, I can always go look at the other side, right? The complementary event is what that really is, 1 minus the complementary event. Right? We're going to go after this one. I bring it up for a variety of reasons, though, because sometimes the calculation that you perform is easier to do in the complementary event than it is in the original event, and that can be a very useful tool as you solve a lot of these exercises. Here we're going to look at probability t is greater than or equal to 8 seconds, so that's the probability that t is equal to 9 seconds, plus the probability that t is equal to 12 seconds, plus the probability that t is equal to 15 seconds. Note that there's no way that the time gap can be simultaneously exactly 9, 12, or 15, so we don't have to worry about intersection events or union events or any of those kind of jazz thing here. These are mutually exclusive events, so we can do the simple addition here, then that makes life a little bit easier in the processing of the numbers. Right? And so the probability that we have exactly a gap of 9 seconds is going to be 3/9, and then for 12 is 2/9, and then of course for 15 seconds is 1/9, and that will then sum up, of course, to 6/9, or 67% chance that we're going to get across safely. Not terribly high, and so that's important for the engineer to think about, that if it takes 8 seconds and we only have a 2/3 chance of making it across safely, that sort of somewhat suggests that we might need to be thinking about putting a signal in. Right? Now, before we head off into another view and version of all this, I want to go back to the classic technique of thinking about these events from the Venn diagram that we all learned about. Well, I learned about it in grade school. I suspect you did as well. But if not, it doesn't really matter, right? The Venn diagram is this idea that we can sort of graphically portray our different possible outcomes or events that we might have. And sometimes that's very useful when we start thinking about how to do these calculations, especially when you start looking at intersections and unions and some weird, difficult combinations of those. And so our Venn diagram is broken up into 5 different events. A 3-second event, or a ball, so to speak, with a 3 printed on there, a ball that's printed with 15, and then we've got then 6 and 12 second potential outcomes, and then a 9-second, where I've intentionally drawn the proportional space on the Venn diagram to be reflective of this relative frequency of 1 to 2 to 3 to 1 to, of the quote balls that I was referring to. Right? And I did that so that we could also make a geometric interpretation of these numbers. Right? That now the probability of safe crossing amounts to being the probability that we throw a dart and it lands in one of these 3 bins. So instead of balls now, we kind of think about this as bin, where the bin is proportionally sized. Right? And so if that geometrically takes up 2/3 of the space, then you can kind of argue that's why the answer is 2/3. That is when we've exactly drawn these geometrically to scale that are consistent with the relative frequencies that we have here in the probability mass functions. Okay. Now there's more games that you can play with that in terms of the ways you could write this kind of a statement. You could write that in terms of unions and intersections, and we're going to do something somewhat similar to that as we get into the next version of this problem, really in the context of conditional probability.